A century of gravitational waves. Beyond Einstein. Why are researchers so intent on proving Einstein right or wrong? It's not simply that he is a towering figure whose name is synonymous with genius, someone whose work has profoundly shaped physics for more than a century. Instead, much of the incentive stems from gravity itself, been something of a problem child in the field. Physicists, including Einstein, have long hoped to devise a unified theory of the universe, but they've struggled to get gravity to mesh with the other fundamental forces. As a result, we currently have a theory of gravity, Einstein's general relativity, and a separate theory of everything else, the Standard Model of particle physics. Unfortunately, these two extremely successful theories are incompatible with each other and sometimes even contradictory. This arrangement just won't do for physicists, who believe there ought to be a single theory of nature that covers everything. Clues for achieving the long-sought unification may come from a better understanding of how and under what circumstances general relativity breaks down. That's why investigators have been pushing the theory to the max, trying to see where it falters in order to figure out the best way to connect gravity with the rest of physics. It's all equivalent. Researchers see the equivalence principle, a central tenet of general relativity, as a promising avenue of attack that could steer them toward an ultimate theory of everything. Simply put, the equivalence principle holds that all bodies under the influence of the same gravitational field experience the same acceleration, regardless of their mass or composition. One advantage of this strategy is that, so far, every credible attempt at crafting a unified theory introduces new forces that would cause ever so slight changes in the way matter interacts with gravity. If these theories are correct, and we look closely enough, we should see EP violations, tiny departures from the equivalence principle. In other words, a gold brick should fall somewhat differently from one made of silver, and a detailed analysis of those differences could provide valuable hints for physicists trying to construct a correct unified theory. We don't know the level at which a violation of the equivalence principle will show up, but we do believe there should be one, says Thibault Damour, a theorist at IHES Institut des Hautes Études Scientifiques, in France. The reason, Damour adds, is that all attempts to unify Einstein's theories with the other forces an endeavor he considers essential to the field lead to EP violations. Experiments conducted on Earth have shown the principle to be valid to a precision of 1 part in 10 trillion. But a space-based experiment called STEP satellite test of the equivalence principle could pose a much sterner challenge, boosting the accuracy of these measurements by a factor of 100,000. That kind of precision could be enough to show physicists just where Einstein's theories start to miss the mark, assuming they do. The next STEP began in 1971 as a thesis project by then graduate student Paul Worden, with Stanford physicist Francis Everett serving on the thesis committee and then as the project's chief scientist soon afterward. Everett has devoted a half-century of his life to testing general relativity and was the principal investigator of Gravity Probe B, a NASA-funded satellite mission that studied, and eventually verified, another aspect of Einstein's theory. By going into space like Gravity Probe B, STEP could dramatically improve the precision of equivalence principle measurements. These measurements are hard to do on the ground owing to vibrations from street traffic, earth tremors, and other disturbances. Space offers a much calmer environment. Another advantage relates to observation time, suggests Towson University physicist James Overdwin, who has worked on STEP, intermittently, since 1999. It drop balls of different size from the Leaning Tower of Pisa, for example, their free fall lasts just seconds. But you can drop things in space, and they never stop falling, Overdwin says, they remain in orbit, constantly falling toward Earth. This allows an extended time, days or longer, to look for some. The plan calls for using 4 pairs of test masses made of at least 3 different materials such as beryllium, niobium, and platinum iridium, which would be kept in a vacuum and cooled to just a few kelvins, reducing temperature fluctuations that can degrade measurement accuracy. Materials are chosen to reflect the broadest possible range of chemical properties so that disparities in acceleration detected by an onboard accelerometer would be the easiest to spot. The point, again, is to make meticulous measurements that show whether objects of different composition fall at different rates. Although years have passed since STEP's inception, Everett hasn't stopped trying to get the project off the ground. The proposed mission received research and development support for decades. It has been endorsed by prestigious review panels assembled by NASA and the European Space Agency, and it has been praised by former NASA head Dan Goldin. But the project has never quite mustered the requisite financial backing, despite Everett's tireless lobbying efforts. Mark Lee, a senior program scientist at NASA, still believes in STEP, calling it one of the most critical fundamental physics experiments that mankind could pursue. The bad news for STEP, he says, is that after 2004, NASA's fundamental physics program was terminated. Since then, it has been only partially revived. Everett remains hopeful, nevertheless. He spent 40 years working on Gravity Probe B before that satellite's launch in 2004. He's also spent 40 years pushing the development of STEP and is not ready to walk away from it yet, even though he just turned 81. Quoting the naval hero John Paul Jones, Everett likes to say, "I have not yet begun to fight." Jones ultimately prevailed during the Revolutionary War, and with luck, STEP might do the same. Perhaps it will be the experiment that finally finds a crack in the heart of Einstein's theory, one that could point us towards something even better, a new, all-encompassing theory of the universe. Defying gravity. Albert Einstein's general theory of relativity remade gravity and solved problems that Newton's theory couldn't. It's passed each of the dozens of experimental tests devised since its debut in 1915. But physicists have barely gotten started. "We've only been playing around it so far," says Neil Cornish, a physicist at Montana State University. That will soon change, though, as several bold experiments enabled by telescopes of unprecedented reach and in some cases by entirely new ways to gather data are poised to study how gravity behaves around some of the universe's most extreme objects. "This is where general relativity really gets going," says Cornish. Powerful telescopes are already looking for minute hiccups in the whirring of stellar corpses called pulsars. A global effort will soon photograph, for the first time, a black hole. And huge gravitators will scan thousands of galaxies for tiny ripples in the cosmic fabric of space-time. Each of these experiments, some of the most ambitious ever conceived, will test a theory that one man worked out a century ago with pencil and paper. Yet most physicists are still betting on that one man. Taking gravity's pulse. With today's advanced instruments, astronomers can for the first time search the universe's gravitational extremes for relativity's possible breaking point. New telescopes and detectors are helping astronomers look far beyond the solar system, where nearly all tests so far have occurred. They aim to detect how gravity behaves in the highly warped regions of spacetime near superdense collapsed stars called pulsars. These extreme objects advertise their presence with intense beams of radiation, sweeping through the sky like cosmic lighthouses, with a regularity rivaling Earth's best clocks. They're so tightly packed that a pulsar the mass of our Sun would be compressed to a sphere with a diameter about the length of Manhattan. One of the more famous general relativity tests to date involved a pair of pulsars, technically named PSRB 1913+16 but better known as the Hulse-Taylor binary pulsar after Russell Hulse and Joseph Taylor, who won the 1993 Nobel Prize in Physics for its discovery. Einstein predicted that as dense objects like pulsars orbit each other, they should create ripples in spacetime, similar to ripples in a lake. Called gravitational waves, these undulations are so tiny that one passing through Earth would joust by far less than the diameter of a proton. Over time, however, the outgoing gravitational waves would deplete a binary system's energy, causing the objects to spiral in toward each other. Over a 30-year study period, the Hulse-Taylor pulsars spiraled toward one another at exactly the rate Einstein predicted. Ever since Hulse and Taylor stumbled upon their pulsars in 1974, astronomers have turned up thousands more throughout the galaxy. One of these recently discovered pulsars, with a highly unusual orbit involving two other stars known as white dwarfs, can now help physicists test a different prediction of general relativity. Scott Ransom and his colleagues at the National Radio Astronomy Observatory are using the Green Bank Telescope in West Virginia to track the rotation of this odd pulsar, designated PSRJ 0337 plus 1715. The system's unique geometry will allow the scientists to examine general relativity's strong equivalence principle, which states that gravity accelerates all objects at the same rate, regardless of their density. When a star collapses into an ultradense object like a pulsar or black hole, some of its matter turns into what's called gravitational binding energy. Part of an ordinary star or white dwarf also exists as this energy, but a much smaller fraction. Einstein's theory predicts that such energy should experience the same gravitational attraction as matter, meaning that Ransom's pulsar and the white dwarf orbiting near it would be drawn toward the system's third star at the same rate. If, by contrast, the rates were to vary, the pulsar's orbit would be distorted, and Ransom and his colleagues could use the timing of the pulses to detect this distortion. In this way, the researchers expect to test whether the strong equivalence principle holds. The results will be 20 times, possibly 100 times or more precise than ever before. Ransom expects the results by mid-2015, but he isn't against Einstein. In all likelihood, general relativity will pass this as well, he says. But we'll never find what, if anything, is wrong with relativity unless we keep trying. Bald black holes. While pulsars are certainly compact objects, the true gravitational Demetrius Psaltis, an astrophysicist at the University of Arizona, is helping to test what may be general relativity's most extreme prediction, that large enough stars will eventually collapse under their own gravity to form these infinitely dense objects. Despite decades of data implying the existence of black holes, all the evidence is circumstantial, based on observations of their effects on light or other objects, Psaltis says. Black holes themselves have yet to be directly observed. Seeing is believing, so Psaltis and his colleagues hope to take a direct photo of Sagittarius A*, the monstrous black hole that suspect lurks at the center of our galaxy. To do this, the researchers will use the Event Horizon Telescope EHT, a combination of more than 10 radio telescopes and telescope arrays scattered across the planet, which should be able to see all the way to the edge of Sagittarius A*, some 26,000 light-years away. Psaltis and his colleagues suspect the black hole will cast a circular shadow amid a radio wave background. In addition to proving that black holes exist, Psaltis says the EHT should also confirm or challenge another key tenet of relativity, the no-hair theorem. The eminent theoretical physicist John Archibald Wheeler quipped that black holes have no hair, meaning they're all identical except for three key distinguishing characteristics: mass, rotation, and a vanishingly small electric charge. Any hair, essentially, any specific information about what goes into the black hole, like an object's chemical composition or molecular structure, or even just shape and size, is lost forever within the black hole's event horizon. With the EHT, Psaltis and his team plan to study the size and shape of the shadow that Sagittarius A* casts. General relativity's no-hair theorem predicts an almost perfectly circular shadow. Modifications to general relativity in which black holes retain their hair could yield an ellipsoidal one. Also hoping to probe the theorem, University of Florida physicist Clifford Wool suggested a test to track how ordinary stars near Sagittarius A* move, and Norbert Wex and Michael Kramer at the Max Planck Institute for Radio Astronomy in Germany hope to do the same with one or more pulsars, though they first need to find one that is close enough. Black hole hair would change how such objects orbit near the hole, and these changes could be detectable by telescopes that will come online within the next decade. If we do find that the no-hair theorem is not satisfied, that would really be a major blow to the theory, or to black holes, says Psaltis. It would be a surprise, he acknowledges, but sooner or later, something unexpected has to show up. And in gravity, like in most places in physics, whenever we open OOCT, we always find a surprise. Gazing at gravity. Finally, one set of experiments will probe relativity not by collecting and analyzing light from cosmological bodies, but by looking at gravity itself. The Laser Interferometer Gravitational Wave Observatory LIGO, and a companion experiment named Virgo will search out those cosmic ripples, or gravitational waves, emanating from galaxies hundreds of millions of light-years away. In the observatory's giant L-shaped facilities, lasers shine down several mile-long tunnels and bounce back and forth between mirrors and into detectors. The observatories are so exquisitely tuned that they can sense the slight push and pull of gravitational waves 1,000th the proton's width of difference on the mirrors. These tiny tugs will create telltale patterns as the detectors collect the laser light. Physicists can then analyze the data for clues about the far-off events that set the undulations in motion. LIGO has operated detectors in Livingston, LA, and Hanford, Washington since 2002. The Virgo detectors in Cassina, Italy, took data in a network with LIGO detectors in 2007 and in 2009 to 2010. None of these efforts detected a gravitational wave, a disappointing, but not unexpected, result. Both the Livingston and Hanford observatories are now wrapping up major overhauls that will allow them to scan 1,000 times more space than before. By 2018, they should be sensitive enough to detect gravitational waves originating from tens of thousands, if not hundreds of thousands, of galaxies, according to physicist and LIGO spokeswoman Gabriela Gonzalez. Data from these waves will test Einstein's predictions about how fast black holes spin and exactly what happens when they smash into neutron stars and into each other. These events will be dramatic. In terms of energy, two merging black holes should outshine every star in every galaxy in the universe in their final moments, says Montana State's Cornish, who studies how to make sense of the data that will soon pour in from LIGO, Virgo, and other gravitational wave experiments. Unexpected signals in the data could force revisions to the theory, Gonzalez says, but she adds, I don't expect we will prove relativity wrong. Still betting on Einstein. Einstein never really doubted general relativity. When asked about the possibility of an early test disproving his theory, he responded, then Anu would feel sorry for the dear Lord. The theory is correct anyway. I agree, based on its track record. Personally, Anu would not be surprised if general relativity survives all of these things, says the University of Florida's Will. If relativity does succumb, it would be exciting, but the exhilaration would be bittersweet. Physicists would have to part with one of their most, one that provides extraordinarily deep insight into the universe from a remarkably economical set of starting assumptions, says Cornish. It really is an incredibly elegant theory. Probing the cosmos with gravitational waves. Gravity literally stalks us to our graves. It underpins the bridges and buildings that make up our cities and the bulk of our transportation systems. It is responsible for holding onto the atmosphere that enables life as we know it. But the ultimate source of this hidden force remains as enigmatic today as when Isaac Newton got beamed by that apocryphal apple. So what hope do astronomers have of routinely observing gravity itself in the same way that they study and observe visible light and the rest of the electromagnetic spectrum? Theory says that gravity creates wave-like ripples in the cosmic fabric. Even the flapping of a sparrow's wings is capable of generating gravitational waves that cause minuscule disruptions of space and time. But scientists' best chance of detecting these perturbations lies on much more massive scales. If researchers could directly observe gravitational waves, they would open the door to the strongest tests yet. Einstein's general theory of relativity, like the endgame in spirals of binary stellar remnant neutron stars, supermassive black hole mergers caused by colliding galaxies halfway across the universe, and even ripples from the Big Bang. Gravitational wave observations would allow astronomers to determine whether intermediate mass black holes actually exist. And on a greater scale, scientists would have the opportunity to detect new and completely unanticipated astronomical sources, as often happens when they investigate a new arena. Propagating radiation, electromagnetic radiation, which is the carrier of almost all the information we have obtained about the cosmos and our place in it over thousands of years of observations, is an oscillation of an electric and a magnetic field that propagates along two axes across space-time. For decades, ground-based detectors also have attempted to observe elusive, weak gravitational waves, which propagate along all three geometric axes z, y, and z and are best thought of as actual oscillations in spacetime itself. They result from mass being accelerated and subsequently disrupting spacetime. Like electromagnetic radiation, gravitational radiation transports energy as waves, which come in an enormous frequency range. Low-frequency waves have long wavelengths, whereas high-frequency ones have short wavelengths. They can span frequencies from near 0 Hz, up to about 100 billion Hz. Different mass sources produce different frequencies of gravitational waves. Stellar mass objects like orbiting white dwarfs or neutron stars produce high-frequency ones, while larger mass objects like the supermassive black holes at the centers of galaxies create low-frequency waves. The strongest signals come from higher mass objects, those that warp the fabric of spacetime more than lower mass bodies. The first hints as early as 1916, Einstein predicted that mass could bend space and time and that gravitational radiation moves, or propagates, but astronomers still haven't directly spied those moving waves. They have, however, measured gravitational radiation indirectly. In 1993, physicists Russell A. Hulse and Joseph H. Taylor, Jr. shared the Nobel Prize for their 1974 discovery of a unique binary star system. They tracked the PIT from a dense stellar remnant of fast-spinning neutron star called a pulsar, over a few months and found that this pulsar, designated PSR 1913+16, orbits a point in space that another invisible neutron star also orbits. Using the pulsed light from PSR 1913+16, Hulse and Taylor calculated both objects' masses and orbits, in addition to their relative orbit. Hulse left astronomy shortly after discovering the system, but Taylor and colleagues continued to observe the pulsar. They saw its short 7.75-hour orbit decaying over time in a way consistent with the emission of gravitational radiation. That energy is, the astronomers think, leaving the system in the form of gravitational waves. Now, after almost 40 years of observations, says Taylor's colleague Joel Weisberg of Carleton College in Northfield, Minnesota, the average distance between the two objects has died 446 feet 136 meters. Some 300 million years from now, the orbits of these two neutron stars will shrink to nothing and the stars will collide. There have been other pulsar systems discovered since our detection that are similar to the one that Hulse and UNA found, says Taylor. But they haven't reached the same level of sensitivity as ours. Connecting and unifying scientists have indirectly detected gravitational radiation in a few systems, but the direct observation of gravitational waves is crucial because we want to understand nature's laws on a fundamental level, and that includes the way gravitational waves may propagate, says Taylor. The biggest question is why the laws of gravity seem to be outside the increasingly unified laws of the rest of the natural world. The basic laws of physics display 4 fundamental forces, 2 nuclear forces, electromagnetism, and the gravitational force, he adds. The first 3 can all be understood in a unified way. It is not consistent with quantum physics. And we don't know why. On an atomic scale, gravity is weak compared to the other forces. But on a cosmic scale, gravity dominates. To date, no mainstream scientific theory has been successful in unifying these two disparate sides of physics. Quantum physics describes elementary particles, says gravitational wave expert Barry Barish of the California Institute of Technology in Pasadena. It predicted the Higgs boson that the European Organization for Nuclear Research just found. Likewise, we know that the general theory of relativity is right. We don't know whether it's Einstein's version or one of its many variants. Scientists' first step is to detect gravitational waves in order to learn more about the force that's behind the ripples. But the ultimate hope is to actually enable researchers to look at the sky in a different way using a different mechanism and to open a new window on the cosmos. We just can't do it as fast as we had hoped, says Barish. Nature's precise clocks, one type of search that astronomers are using to find gravitational waves, targets pulsars, but not like the studies that Taylor and Weisberg are doing of a binary system. Instead, several international groups of scientists track millisecond pulsars, which complete hundreds of rotations every second. Their spins are stable, so astronomers look for minuscule changes in these precise clocks due to the effects of background gravitational waves as they pass near Earth. The North American Nanohertz Observatory for Gravitational Waves uses Puerto Rico's Arecibo dish and the Green Bank Telescope in West Virginia. The project is part of an international pulsar timing array network that works with Australia's Parkes Pulsar Timing Array and the European Pulsar Timing Array. Millisecond pulsars likely have been spun up in binary systems. The pulsar companion has evolved into an expanding giant, and some of its mass has been accreted onto the pulsar, spinning it up, says Nanograv team member Ingrid Stairs, an astronomer at the University of British Columbia in Vancouver. But to spin up to a millisecond rotation, can still take a billion years or so. We do long-term pulsar monitoring and look for correlations in the signals over the course of several months or a few years, says Stairs. Space-time around Earth will be distorted a little in one direction or the other. A pair of pulsars close together on the sky might have their signals come earlier or later in a correlated way. That's due to the gravity waves passing near to Earth. Scientists are looking for variations in the pulsar signals down to tens of nanoseconds, which could be caused by random background gravitational wave signals from many different supermassive black hole collisions. Only in the past decade has it seemed feasible to accomplish the timing at the level needed to detect gravitational waves accuracies of 100 nanoseconds or less for a few dozen targeted pulsars. We're still not there, says Stairs. Nanograv is most likely to detect gravitational waves from pairs of merging supermassive black holes during their last breaths as they spiral into each other with orbital periods of only around a year. These would produce the longest wavelength and lowest frequency gravitational waves because of their huge masses and accelerations, the type that nanograv is sensitive to. The astronomers expect to detect gravitational waves that have frequencies of nanohertz 10^9, which correspond to wavelengths of years. That's about 15 orders of magnitude slower than a typical AM band radio signal. We hope to make a gravity wave detection in the next few years, says Stairs. After detection, their next goal would be to get values for the signal strength at different frequencies, which would enable the team to learn more about the wave's sources. Other current equipment, the Laser Interferometric Gravitational Wave Observatory LIGO, at a cost of $360 million, is the most ambitious ground-based gravitational wave direct detection effort to date. The joint Caltech-Massachusetts Institute of Technology project spent nearly 5 years searching for high-frequency 10 Hz to 10,000 Hz gravitational radiation and is now undergoing a $205 million upgrade. Potential gravitational wave sources that might be detectable for the ground-based instrument include binary pulsars in the process of collision, stellar mass black holes in the process of mergers, core collapse-type Doi supernovae, and even shifts of the surfaces of neutron stars. LIGO consists of a Hanford, Washington, facility that houses a 0.5-mile-long 4.0 km detector and a 1.2-mile-long 2.0 km detector and a Livingston Parish, Louisiana, facility with a 2.5-mile-long 4.0 km detector. Each instrument uses two long laser arms perpendicular to each other to form an L shape. Laser light flows through LIGO's lengthy vacuum tubes. The light waves are carefully misaligned so that their troughs and crests interfere to create dark fringes, ensuring that no light hits LIGO's photon counter. Gravitational waves that pass through at angles perpendicular to the arms would laser light in one arm and shorten it in the other. This detection method revolves around destructive interference of the laser light itself. A passing gravitational wave momentarily would cause the laser light to interfere constructively and allow a few photons through to a counter that sits on a hanging test mass. Those photons would thus register as a gravitational wave detection. While LIGO didn't find any gravitational waves during its initial run, which ended in 2010, the observatory's searches were considered successful enough for an upgrade that should increase the detector's sensitivity by a factor of 1,000. Caltech experimental physicist and LIGO chief scientist Stan Whitcomb notes that for the past few years, the LIGO team has been in the process of upgrading mirrors, increasing laser power, and changing the test masses and suspension systems before beginning data-taking runs at less than full sensitivity late next year. Both Italy and Germany also host ground-based gravitational wave detectors. Virgo, an instrument near Pisa, Italy, is a laser interferometer equipped with 1.9-mile-long 3 km, perpendicular arms that began collecting science data in 2007. This project hasn't yet detected any elusive gravitational wave, but the European Gravitational Observatory, which operates Virgo, is upgrading the detector. It should be complete by the end of 2015. Meanwhile, GEO600, a German and UK gravitational wave interferometer near Hanover, Germany, has 6 60-yard LROM arms. It has done several science runs in concert with LIGO and has been partially upgraded. Some scientists, however, consider GEO600 more of a research and development project than a detector with a real shot at observing gravitational waves. Global limitations. This current ground-based detectors is just on the cusp of gravitational wave detection capabilities and are inherently hamstrung by background noise here on Earth. One of the main limitations for building an Earth-based detector, says Gregory Harry of American University in Washington, D.C., is that below 10 Hz, it's almost impossible to see anything due to all the ground motion from people, traffic, geology, and wind. Harry is past chair of LIGO's optics working group. In space, there isn't as much noise, so it's easier to detect low-frequency waves, but it's difficult to achieve the large amount of laser power needed for greater sensitivities at high frequencies. So to probe the high frequencies, Whitcomb envisions a global gravitational wave detector network by 2025, the new generation of high-sensitivity ground-based interferometers. He says this will enable researchers to truly coordinate observations between gravitational wave observatories and electromagnetic telescopes. The goal is to coordinate the observations so that by timing the gravitational waves' arrival at various ground-based detectors, astronomers can better determine the waves' astrophysical origins. Learning more about the population of black holes in the universe, how they formed, how they merged to cause the growth of galaxies is what's most exciting about gravity wave research, says Whitcomb. There's a lot of speculation and almost about those processes. Venture to space gravitational wave scientists have long been plotting a move into space. In the early 1990s, the European Space Agency ESA and NASA proposed a joint mission, the Laser Interferometer Space Antenna LISA. Since then, the project has evolved tremendously. NASA is no longer a partner, and ESA will go ahead with a 2034 space-based gravitational wave observatory with a possible small contribution from NASA. The project has been scaled down, and the evolved LISA mission is a leading contender, but concepts won't official 2034 mission for several years. Carsten Dantzmann, director of Germany's Max Planck Institute of Gravitational Physics in Hanover, says LISA's current architecture still resembles the plan he helped put forth in the 1990s. LISA's envisioned architecture involved 3 cylindrical 5.9-foot diameter 1.8 m spacecraft whose sun-orbiting positions would mark the vertices of an equilateral triangle 3 million miles 5 million km per side. LISA instead would consist of a mother spacecraft and 2 daughters in a V-shaped pattern 0.6 million miles 1 million km per side. While these changes essentially decreasing the size of the observatory by a factor of 5 mean the mission would be less sensitive, it becomes financially doable for a single space agency. The observatory would fly 1 Earth-Sun distance from our star, trail our planet by some 12 million to 30 million miles 20 to 50 million km, and be inclined 60 degrees from the plane of the solar system. LISA would use 2 1-watt infrared lasers and compare how the light waves interfere, in a manner similar to LIGO, to look for gravitational radiation. Both a LISA and a full-scale LISA mission would be sensitive to frequencies spanning a millihertz up to a tenth of a hertz, which correspond to wavelengths of 200 million miles 300 billion km, and 2 million miles 3 billion km, respectively. Such lengthy waves likely have their origins in binary white dwarf systems within our Milky Way galaxy, during the mergers and collisions of supermassive black holes at the centers of other galaxies, and, perhaps if astronomers get lucky, from the Big Bang itself. Either observatory would detect gravitational radiation by sensing variations in the distance between free-flying proof masses gold-platinum polished cubes about 1.6 inches 4.0 centimeters, on a side that would be drag-free in a vacuum inside each of the three spacecraft. Scientists would measure the position of each proof mass. The cubes would be magnetically clean and thus would react nearly negligibly to magnetic fields or bombarding particles from the Sun, which would be difficult to differentiate from gravitational wave interactions. The basic idea, says Harry, is that the mass would move around in space due solely to gravitational forces. The observatory would use thrusters to maneuver each spacecraft around the free-falling cubes. We have until 2020 to refine the details, says Dance Man, and we all hope that NASA will be on board so that we can enhance the capabilities beyond what could be afforded as an ESA-only mission. If NASA agrees to participate, the ELISA mission concept could evolve back to the original LISA plan. Just within the first few months of observations, astronomers expect a LISA-like mission to detect thousands of gravitational wave sources. These include ultra-compact neutron star binary systems, supermassive black hole mergers, and in spirals of stellar mass black holes into supermassive black holes. ESA will launch its LISA Pathfinder mission, a single spacecraft that will test a full-scale mission's most crucial technologies, in mid-2015. These include laser interferometry, free-flying proof masses, drag-free control mechanisms, magnetics, and noise levels. To the beginning to directly detect gravitational waves from the scream of the Big Bang, astronomers have to look further to the future. As part of its Beyond Einstein program several years ago, NASA funded a concept study to determine what it would take to lift the Iron Curtain on the beginning of time itself to push cosmology's look-back times to epochs that are even earlier than the first light detection of the cosmic microwave background CMB, typically dated to about 380,000 years after the Big Bang. This primordial radiation, evidence of the time when electrons and nuclei combined and light could travel freely, fills the cosmos. The study detailed a Big Bang observer mission that would launch perhaps as early as mid-century. It would be similar to LISA but much more ambitious and entail 3 constellations of spacecraft instead of just 3 spacecraft. The satellites also would orbit the Sun but would investigate wavelength frequencies between 0.1 and 10 Hz, the range between a LISA-like mission and ground-based interferometric detectors. According to Harry, who was a definition team member for NASA's Big Bang Observer study, the gravitational waves from the Big Bang most likely will be random and span enormous wavelength ranges, from the order of the size of the observable universe down to thousands of kilometers or even smaller. Terrestrial gravitational wave detectors like the upgraded LIGO could see all of these, in theory, too. These gravitational waves allow astronomers to see back to the period of hyperacceleration called inflation, from 1036 seconds after the beginning of time. Even earlier events in the universe, the Big Bang itself, could have produced gravitational waves, too. If scientists could find these waves, they might provide information about fundamental interactions of particles at energy scales far beyond those of particle accelerators on Earth. While directly seeing these primordial waves is still decades away, just a few months ago, cosmologists announced that they saw the imprint of inflation's gravitational waves in the CMB. This swirling pattern, seen by the BICEP-2 instrument that observes from Antarctica, is a remnant from those wrinkles in extreme early space-time. But this discovery, if verified, is still an indirect observation of primordial gravitational waves. The furthest back in time scientists can see so far is the CMB. There's a fairly large gap between the true beginning and the cosmic microwave background, says Harry. We know so going on then that any sort of data that could be seen would be incredibly valuable. However, Taylor says, even if there were a putative detection of such ancient gravitational waves, it would be tough to determine that they were actually generated by the Big Bang or by cosmic inflation. The signals would not have a characteristic that tag them with a name and tell you where they came from, he adds. Even so, as Danceman points out, once scientists are truly able to use gravitational radiation for everyday astronomy, it will bring about a sea change in the field. Propagating undisturbed at the speed of light, eternally traveling through the universe, gravitational waves, will revolutionize astronomy, he says, unveiling a world that we have no other chance of observing. Black holes in our backyard. Black holes are the most astounding objects in the universe. And at least 19 of them lurk within the Milky Way. Until Swiss astronomers Michel Mayor and Didier Clauze discovered the first planet orbiting a Sun-like star in 1995, scientists faced a dilemma. Thought such planets should be common, but they had no proof. Fast forward 17 years and the verdict is in the number of confirmed exoplanets now totals several hundred and should pass the 1,000 mark in the next year or two. The discovery of black holes followed a similar trajectory. By the early 1990s, most astronomers suspected these bizarre objects existed, but confirmation was hard to come by. Scientists like to say that extraordinary claims require extraordinary proof, and things don't get much more astonishing than black holes. These bodies possess a gravitational pull so powerful that nothing, not even light, can escape their clutches. Information about what happens inside a black hole can never leave a cosmic equivalent to Las Vegas. Fortunately, the suburbs of Vegas are more forgiving. Material in a black hole's vicinity suffers conspicuously from the intense gravity. Wayward stars move fast, and gas becomes superheated and radiates copious amounts of light. Astronomers confirm a black hole's existence when they see these signatures and can eliminate all other possible causes. In the past 15 years or so, the tally of black holes in our galaxy has reached 1918 reside in X-ray emitting binary star systems, and one lurks in the Milky Way's core. But many more likely remain beyond astronomers' current reach. From Newton to Einstein in the late 1700s, British professor John Michell and French astronomer and mathematician Pierre-Simon Laplace advanced the idea of what Laplace called dark bodies. Using Isaac Newton's concepts of light and gravity, they reasoned that the gravitational pull of a massive star could be large enough to prevent light from escaping. Unfortunately, Newton's theory could not describe what happens when gravity grows this strong. That understanding wouldn't come until Albert Einstein developed his general theory of relativity in the 1910s. Relativity, which treats gravity as a distortion of space-time, allows physicists to describe black holes in gory detail. Still, it took decades before most scientists considered these objects more than theoretical curiosities. The reality of black holes began to emerge once astronomers understood how massive stars die. If a star begins life with more than about 8 times the Sun's mass, it will not experience a quiet demise. When such a star exhausts its nuclear fuel, its core collapses. This triggers a shock wave that destroys the rest of the star in a brilliant supernova that can shine with the light of 10 billion suns. In most cases, the core left behind weighs between 1.4 and 3 solar masses and has been crushed into a sphere the size of a major city. A single teaspoonful of this so-called neutron star would weigh close to 1 trillion tons. Yet even this exotic end state pales in comparison with what happens to the rarest of stars that start life with more than 30 solar masses. In 1939, physicists J. Robert Oppenheimer and Hartland Snyder showed that when such a star dies, its collapsed core, which weighs more than 3 suns, is too heavy to settle down as a neutron star. It creates a region of space-time cut off from the rest of the universe because no light can ever escape. 30 years later, physicist John Wheeler coined the descriptive term black holes for these objects. Black holes possess only 3 characteristics: mass, spin, and charge. All other properties of the collapsing star are lost. And because stars rarely have any excess positive or negative charge, mass and spin describe most black holes. A key feature of a black hole is its event horizon, the radius at which a beam of light would just fail to escape. Any event that takes place within this horizon can never be glimpsed from outside. For a non-spinning, 10 solar mass black hole, the event horizon spans approximately 37 miles 60 kilometers. Double the mass, and the diameter also doubles. A black hole spinning at the mass has a diameter half that of a non-rotating one with the same mass. The galaxy's black holes. Because telescopes cannot see inside the event horizon, astronomers must search for a black hole's impact on its immediate surroundings. Some binary star systems offer a perfect environment. The massive stars that create black holes evolve quickly, typically running through their nuclear fuel in a few million years. After the star explodes, the companion usually survives. The black hole's intense gravity may pull material from its neighbor's outer layers. This gas falls toward the black hole and forms an accretion disk that swirls around the invisible object like water circling a drain. As the material moves ever faster, friction among the atoms heats it to millions of degrees. Gas at this temperature emits lots of X-rays, which Earth-orbiting observatories can detect. So, to detect a black hole, astronomers look for an X-ray emitting binary system comprising one normal star and an invisible but massive companion. Lots of these objects exist anyway, but not all contain black holes. Neutron stars in a binary can produce the same behavior, and because they radiate little light, they can't be detected across large distances. To differentiate between the two possibilities, astronomers need to pin down the compact object's mass. Generally, that a stable neutron star can't weigh more than 3 suns. Any invisible companion bigger than that must be a black hole, assuming, as almost every scientist does, that relativity accurately describes such strong gravitational fields. To find the object's mass, astronomers must measure the binary system's orbit precisely. Ronald Millard of the Massachusetts Institute of Technology in Cambridge and Jeffrey McClintock of the Harvard-Smithsonian Center for Astrophysics, also in Cambridge, have compiled the most up-to-date list of black holes in binary systems. Our galaxy contains 18, their locations and properties appear on page 49. But this list likely forms only the tip of the iceberg. Millard and McClintock count 20 more binary systems that show similar X-ray signatures but have no detailed orbital information to provide masses. Astronomers haven't even seen an optical counterpart in most of them, and nearly every scientist suspects greater numbers of black holes exist either alone in space or in more widely separated binaries that don't emit X-rays. Astronomers estimate that the Milky Way holds between 100 million and 1 billion black holes. The swan song, the most famous stellar mass black hole, is Cygnus X1. Its designation signifies it as the first X-ray source discovered in Cygnus the Swan, which lies some 6,100 light-years from Earth. It is the only one in a high-mass X-ray binary system. Its companion star is a blue supergiant that tips the scales at approximately 19 solar masses. In fact, this luminous companion shines brightly enough that it appears in our sky as a 9th magnitude star visible through amateur telescopes. See track down a black hole on page 46. The black hole in Cygnus X1 weighs close to 15 solar masses, which makes it the heaviest one known in a binary system. The two objects orbit each other once every 5.6 days at an average distance about half that between the Sun and Mercury. As matter in the accretion disk falls toward the black hole, magnetic fields channel some of it into a pair of high-speed jets that emerge perpendicular to the disk. Recent observations show that the black hole rotates at more than 90% of the theoretical maximum. The other 17 stellar mass black holes reside in low-mass X-ray binaries. Most of their companion stars have masses similar to or somewhat smaller than the Sunday. Still, a few of these objects stand out. Astronomers estimate the mass of GRS 1915 + 105, a designation that comes from Granot satellite, and the object's sky coordinates, in Aquila at 14 suns, but with an uncertainty of 4 solar masses, it could be the heavyweight champ. This object also spews jets that appear to travel faster than the speed of light, an optical illusion that arises because the jets move at about 90% light speed toward Earth. It marked the first time scientists had seen such superluminal motion within our galaxy. Meanwhile, GX 339-4 lies in the southern constellation Era and experiences frequent X-ray outbursts followed by periods when its emission decreases, but never so far as to let its companion star shine through. It's the only binary black hole whose companion still eludes detection. Just because a binary system behaves oddly doesn't mean it possesses a black hole, though. Few objects in the galaxy sport the peculiarities of the high-mass X-ray binary SS-433, which lies inside a 10,000-year-old supernova remnant called W50. The explosion that created this glowing remnant gave birth to a compact object that now steals material from a massive companion star. The gas forms an accretion disk that powers two jets beaming in opposite directions like a pair of rotating lighthouse beacons. Many astronomers think SS-433's compact object is a black hole, but they can't rule out a neutron star. Black holes in globulars? The biggest stellar mass black holes in our galaxy appear to top out at about 15 to 20 times the Sun's mass. Yet a number of scientists think much larger ones exist in some of the galaxy's 150 or so globular star clusters. Star-sized black holes likely formed in these clusters early in their histories, more than 10 billion years ago, and fairly quickly sunk to the center. But what happened to these black holes? Some think that they merged with other black holes or neutron stars and grew much bigger, while others suspect that they encountered other stars that then ejected them from the cluster. Thomas Macarone of the University of Southampton in England and his colleagues reported in 2007 on the best candidate for a black hole in any globular cluster. They found an X-ray source in a globular circling the giant elliptical galaxy M49, located some 50 million light-years away in the Virgo cluster. The object emits far too many X-rays to be a neutron star and so must be an accreting black hole. Its mass exceeds 20 suns but could be much higher. The case for black holes in our galaxy's globulars is more tenuous. Unless a black hole actively feeds on material from another star, it won't have an accretion disk that glows in X-rays. The best alternative method is to look at the brightnesses and motions of the stars near a cluster's center. Several research teams have examined its largest globular, Omega Centauri, to do just that. In 2008, a group led by Eva Noyola of the Max Planck Institute for Extraterrestrial Physics in Germany reported a black hole weighing 40,000 solar masses. Just 2 years later, however, J. Anderson and Roland P. Merrill of the Space Telescope Science Institute in Baltimore, Maryland, found no evidence for a black hole of that size. At this stage, neither side seems to be winning the debate. A similar argument rages over the relatively nearby globular M15 in Pegasus. Some researchers claim the presence of an intermediate mass black hole weighing about 4,000 suns, while others find no such evidence. Earlier this year, Jay Strader of the Harvard-Smithsonian Center for Astrophysics and his colleagues announced that new observations show M15 can't have a black hole larger than 980 solar masses. The beast in the middle. While strong evidence for intermediate mass black holes is lacking, the same can't be said for their big brothers. Astronomers have found compelling signs for a supermassive black hole in the center of almost every large galaxy they have scrutinized, and the Milky Way is no exception. The core of our galaxy harbors an object called Sagittarius A*, pronounced A star, a black hole with about 4 million times the Sun's mass. It's the 19th confirmed black hole in the Milky Way, and it sits dead in the center. The evidence takes several forms. First, intense radio waves flow from an accretion disk that spans a region no bigger than our solar system. But the proof comes from careful tracking of the motions of stars as they orbit the central mass. It's the same method astronomers use to hunt for globular cluster black holes, but the huge size of the object in the Milky Way's heart makes these motions far easier to see. Analyzing the stellar orbits leads directly to the black hole's mass. The count of black holes in our galaxy likely will continue to grow in the years ahead, but it never will outpace the flood of planet discoveries. The ability to find planets has reached the stage where it's surprising when a week goes by without a new detection. Black holes hide their identities much better, either behind the cloak of an event horizon or in isolation from other objects. Perhaps the biggest surprise in the study of our galaxy's black holes is that we've already found punctual noirs. 20 things you didn't know about gravity. Punctual anu. Star Wars Obi-Wan Kenobi said the Force surrounds us and penetrates us, it binds the galaxy together. He could have been talking about gravity. Its attractive properties literally bind the galaxy together, but it also penetrates ending physically through us, keeping us bound to Earth. Punctual doi. Unlike the Force, with its dark and light sides, gravity has no duality. It only attracts, never repels. Punctual trei. NASA is trying to develop tractor beams that could move physical objects that would trump gravity. Punctual patru. Passengers on amusement park rides and the International Space Station experience microgravity, incorrectly known as zero gravity, because they fall at the same speed as the vehicles. Punctual sinsi. Someone who weighs 150 pounds on Earth would if it were possible to stand on Jupiter weigh a whopping 354 pounds on the enormous gas giant. Larger masses have greater gravity. Punctual sase. To leave Earth's gravitational pull behind, an object must travel 7 miles a second, our planet's escape velocity. Punctual sapt. Gravity is by far the weakest of the 4 fundamental forces. The other 3 are electromagnetism, weak nuclear force, which governs how atoms decay, and strong nuclear force, which holds atomic nuclei together. Punctual opt. A dust magnet has enough electromagnetic force to overcome all of Earth's gravity and stick to the fridge. Punctual noir. An apple didn't hit Isaac Newton in the head, but it did make him wonder if the force that makes apples fall influences the moon's motion around Earth. Punctual z's. The apple in Newton's eye led to the first inverse square law in science, F equals G asterisk mm/R2. This means an object twice as far away exerts a quarter of the gravitational pull. Punctual unspries. Gravity's inverse square law also means the reach of gravitational attraction is technically infinite. Whoa. Punctual doispries. Gravity's other definition, meaning something weighty or serious, came first, originating from the Latin gravis, or heavy. Punctual trispries. The force of gravity accelerates everything at the same rate, regardless of weight. If you dropped balls of the same size but a rooftop, they would hit the ground at the same time. The heavier object's greater inertia cancels out any speed it might have over the lighter object. Punctual paespries. Einstein's general theory of relativity was the first to treat gravity as a distortion of space-time, the fabric that physically embodies the universe. Punctual synspries. Anything with mass warps the space-time surrounding it. In 2011, NASA's Gravity Probe B experiment showed Earth tugs on the universe around it like a wooden ball spinning in molasses, exactly as Einstein predicted. Punctual sysprees. When distorting the space-time around it, a massive object sometimes redirects light that passes through it, just as a glass lens does. Gravitational lensing can effectively magnify a distant galaxy or smear its light into a strange shape. Punctual saptisprees. The three-body problem, determining all the patterns 3 objects orbiting each other could take if influenced only by gravity, has puzzled physicists for 300 years. So far they've found only 16 types of solutions, 13 of them just discovered this March. Punctual optisprees. Although the other 3 fundamental forces play nice with quantum mechanics, the science of the very small gravity is stubbornly incompatible with it. Quantum equations break down if they try to include gravity. How to reconcile these 2 completely accurate but opposing descriptions of the universe is one of physics' biggest questions. Punctual noirsprees. To understand gravity better, scientists are looking for gravitational waves, ripples in spacetime that result from things like black holes colliding and stars exploding, according to Amber Stuver, a physicist at Louisiana's Laser Interferometer Gravitational Wave Observatory LIGO. Punctual dwasi. Once LIGO researchers successfully detect gravitational waves, they'll be able to use them to see the cosmos as never before. Every time we've looked at the universe in a new way, Stuver says, it revolutionized our understanding of the universe. Talk about heavy.